So in the last session, we've been talking about a group action on a set. And we also defined when does a group acts on a set faithfully, and when X is a G set, when does it become transitive. And we did some examples also, but we are going to do more examples on this. But before that, we need some more definitions. So let X be a G set. Then we are interested in two subcollections, one from X and one from G, a subset of X and a subgroup of G. So let G belongs to G is a fixed element in G. Then define XG. It's a fixed set on G. There are elements from X such that G fixes X. It's called fixed set. And for a fixed X belongs to X, define Gx as G belongs to G such that Gx equal to X. X is fixed by those elements of G. So the first claim is Gx is a subgroup of G. How do you prove a subset of a group is a subgroup? See whether it is closed and should exist a identity, and for every element there should be an inverse. So let us take two elements from here. So let G1 comma G2 belongs to Gx. And that implies, with this definition, G1x equal to G2x is equal to X. And that implies G1 G2x is equal to, this is X, G1x, and that is equal to X. And that implies G1 G2 belongs to Gx. And E belongs to Gx because Ex equal to X. That is the definition of group action. And if G belongs to Gx, that implies Gx equal to X, and that implies X equal to G inverse of X, and that implies G inverse belongs to Gx. And that implies Gx is a subgroup of G. And this subgroup is called isotropy subgroup of X. Under the action of G on X. So our next definition is an orbit. So let X be a G set. Then define a relation on X such that x1 comma x2 belongs to X and x1 is related to x2 if there exists a G in G such that x1 equal to gx2. That means these two elements can be related via an element in X, an element in G. x2 can be reached from x1 via G. Then this relation is an equivalence relation, meaning it is reflexive, symmetric and transitive. So let's prove that. So the relation is reflexive because X is equal to EX and that implies X is related to X using that rule. X is symmetric because x1 related to x2 implies x1 is equal to gx2 for some G in G, and that implies x2 equal to G inverse of x1 and G1 for G1 it belongs to G, that implies x2 is related to x1. Is transitive because x1 related to x2 and x2 related to x3 implies x1 is equal to G prime x2 and x2 is equal to G double prime x3 for x prime, G prime, G double prime belongs to G. And that implies x1 is equal to G prime, G2 is G double prime x3 and that is equal to G double prime x3 and that is equal to G x3 where G is equal to G prime, G double prime, and that implies x1 is related to x3. And that implies the relation is an equivalence relation. And what does the equivalent relation in a set do? It splits the X into disjoint classes. So this relation divides X into disjoint subset called classes. That is a property of an equivalence relation. These classes are called orbits. And is denoted by Gx, not the subscript x. Subscript x is a different one. That is actually an isotropic subgroup. So this orbit is denoted by Gx. So this is an orbit containing x. So I have a action table here. I'm going to explain what it is. This is to give you an example or demonstrate the concept of a G set and when it is going to be transitive and whether it is acting on a set faithfully, and we are going to find out some orbits and fixed sets. Then we are going to find some isotropy subgroups. So we are going to do all this stuff using this example. So let me explain what this table is about. We already know there is a dihedral subgroup of the symmetric group of element 4, that is D4, and it contains 8 elements: sigma 0, sigma 1, sigma 2, sigma 3, and this is mu 1 and mu 2, delta 1, delta 2. We already know about this. So this is our group. So we need a set. That set is actually, I'm going to write it here. That set is the parts of a square. So vertices are numbered as 1, 2, 3, 4. And the midpoints of these sides are marked as P1, P2, P3 and P4. And this side is S1, this side is S2, this side is S3 and this side is S4. And this diagonal is D1 and this diagonal is D2, and this line is the midpoint of P1 and P2, it is M1, and the horizontal this thing is M2, and the point at the center is C. So our set X is the points vertices 1, 2, 3, 4. Then I will write it a little towards this side. Our X is 1, 2, 3, 4, those are the vertices, and we have sides and midpoints of sides and center of the square and two diagonals and one horizontal division, that is M1, vertical is M1 and horizontal is M2. So 4, 4, 4, 4, 16, 17, those are these elements. So this is our X and this is our it's D4, I'm going to write it as G. These are group elements and these are the elements from the set. And this set is a D4 set. And we haven't defined the action on it, but we are going to define the action. See, the way we are going to define is that this is the identity. So this is not going to move any of these elements. So if you see sigma 0, it keeps as it is without any change. Sigma 1 operating on this X would be the elements of the square when we rotate this vertex to anti-clockwise direction to 2, that is 90 degrees. So 1 will go to 2, 2 will go to 3, 3 will go to 4, and 4 will go to 1. And that is what this one, 3, 2, 4, 1. Similarly, S1 will go to S2, S2 will go to S3, and S3 will go to S4, and S4 will go to S1. And that is this. And similarly, mu1 will be the vertical shift. 1 will go to 2, 4 will go to 3. And similarly, all the parts will turn like that. So mu1, 1 will go to 2, and 2 will go to 1. 3 will go to 4, and 4 go to 1 will go to 2, 2 will go to 1, 4 will go to 3, 3 will go to 1. Mu2 will be the horizontal shift, horizontal transformation. So 1 will go to 4, and 4 will go to 1, 2 goes to 3, 3 goes to 2. The delta 1 goes to 3, meaning you are shifting, you are taking the image on this diagonal. So 1 goes to 3, but 4 and 2 are fixed. 1 goes to 3, 2 is fixed, 3 goes to 1. And similarly, if you take the image on the other diagonal, you will get this. So that is how this action table is prepared. So this is actually, this is a group, and this is a group. This is a set of some elements: vertices, sides, diagonals, center, and all. Now let us start. See whether so X is a D4 set. So let us see whether this action is faithful. So for that, the homomorphism phi from D4 to Sx. Sx means the permutations on here. Okay, there are several permutations on X. We have 17 elements. So we are looking for all the permutation in Sx. So we are defining a map from D4 to the collection of all permutations, defined by phi of, take an element from here. I'm going to write it as G for time being. It is not G, but this is a group, so I'm going to take it as a group, is equal to sigma G. This sigma G is an element of Sx, meaning it's a permutation on X, defined by this is a function from X to X defined by sigma G of X equal to Gx. So that is the definition of this phi. And we need to show that this is 1, 1, or the kernel is the identity of this. That is what we want to find out whether it is. So kernel of phi is equal to, the element belongs to D4 such that phi of G is equal to the identity of Sx. Identity of Sx means what? It is the permutation that keeps the element as it is. And there is only one element in D4 that keeps the element as it is, and that is sigma 0. And this is equal to sigma 0. And that implies phi is 1, 1, and that implies phi is, that implies D4 acts on X faithfully. Our next question is this action transitive? The answer is no, because there is no element in D4 that maps a vertex to a side. Vertex and sides are elements of X. If action is transitive, any element can be reached to any element using one of these group elements, group actions. If you take 2 and 3, S3, there is no way we can reach 2 to S3 using this table. We can reach from 2 to 3 and 3 to 4 in several ways. But 3 to S3 or 2 to S3 or 2 to S1 we cannot reach using one of these elements from D4. So this is not transitive. Now let us find out the fixed set. Let us say X sigma 2. What is the definition of the fixed set? X sigma 2 are elements from X such that sigma 2 of X equal to X. So sigma is sigma 2, this is sigma 2. sigma 2 should keep the elements as it is. So it will not be any of these vertices, and it will not be this one, it won't be any of this, but the diagonal M1 and M2 and D1 and D2 and C, that are the only diagonal M1, M2, D1, D2 and C. Meaning sigma 2 of M1 is M1. Sigma 2 of M1 is M1. That is how we define. We will take another one. Mu of delta 1. X belongs to X such that delta 1 of X should be equal to X. So delta 1. So this, none of this. Okay. This is actually delta 1. You have 2 and 4. 2 and 4. Delta 1 of 2 is 2. Delta 1 of 4 is 4. Delta 1 of 2 is 2. Delta 1 of 4 is 4. Then no. This one D1 and D2 C. D1, D2, C. And that's it. So these are the fixed set of delta sigma 2 and delta 1. Now let us find out the isotropy subgroups. Let us find out the isotropy subgroups of D4. Namely, let us take G of let us take G3. So what is this? This is defined by elements from D4 such that G3 is equal to 3, or sigmas from D4 so that sigma of 3 is equal to 3. So if you take this column, the elements that retains 3 is sigma 0 and delta 2. So this is actually a subgroup of D4. Now I will take another one, DM1. So if you take M1, the ones which retains M1 is definitely sigma 0, then sigma 2, then mu 1, then mu 2. Yeah. So these are the isotropy. Let us take one more, GS2. GS2. So sigma 0, definitely the identity element will be there. S2, this is going to be mu 2. Those are the only elements, nothing else. So this is the isotropy subgroup of S2. Now let us find all the orbits of this. Let us find the orbits in X as a D4 set. When X is a D4 set, what are the orbits in X? What is the definition of an orbit? It is a subset of disjoint subsets of X that is formed by the equivalence relation. See, if X1 is related to X2, if there exists a G in G such that X1 is equal to GX2. This is the relation. So, the class containing 1 cannot have anything beyond that. You don't see any ones here. You will see only ones in this column, in these 4 columns. So, one class is 1, 2, 3, 4. And this is the class containing either 1, 2, 3 or 4. Similarly, S1, S2, S3 and S4. This is another orbit. And M1, M2, another orbit. D1, D2, another orbit. C is a singleton orbit. Then P1, P2, P3 and P4. If you take an orbit, the elements inside the orbit should be reached from any other elements in that orbit using one of the elements from the group, and that is the definition. So the orbits in this X are these. I want to define one more term here. Definition. Let X and Y be two G sets. Same group but two sets. G acting on two sets. Then X is isomorphic. X is an isomorphic G set to Y if there exists a map phi from X to Y such that for every G in G, phi of Gx is equal to G of phi x. See here Gx is an element in X and you map that element in Y. So this is an element in Y. Here this is an element in already in Y, and Y is a G set, so this is also an element in Y. So this has to be equal for every G. Then X is isomorphic to Y. Normally there is no isomorphism between two sets, but we have a group acting on these two sets, and that is how we are going. That is why we are defining the isomorphism here. Now let us see this isomorphic G sets using this example. So let us take two subsets of X, X1, S1, S2, S3 and S4, and X2 as P1, P2, P3 and P4. Now we can see that X1 and X2 are D4 sets. if you define a map from phi to x1 to x2 by phi of Si is equal to Pi, it's easy to show that phi is an isomorphism. You know why? Because if you take these two columns, this set of column and this set of columns, they behave exactly same. S1, S2, S3, S4, P1, P2, P3, P4, S2, S3, S4, S1, P2, P3, P4, P1. It is not just there are only 4 elements here and 4 elements here, but this behaves exactly like this on the group elements. So that is why we will say that phi is an isomer, not because x1 and x2 has same number of elements. It behaves exactly like the similar elements under the map, under the group elements. So they are isomorphic. They are isomorphic G set, D4 sets. Let us take another 2 subsets. Let us take x3 as 1, 2, 3, 4 and see whether x3 and x1 are easy. This is also a D4 set, but x1 and x3 are not isomorphic because actually D1 fixes 2. Okay, D1 fixes 2 and 4. Delta 1 because delta 1 fixes 2 and 4 in x3, but delta 1 does not fix any element in x1. See, if you take a delta 1, if you have the same map here, let us say 1 to S1 or I to Si, if that is a map you are going to consider, then phi of 2 under delta 1 is what? This is phi of 2 is delta 1 of phi of 2 is S2. Delta 1 of S2 is S1. But phi of delta 1 of 2, delta 1 of 2 is 2. So phi of 2, and that is S2. So this definition doesn't hold, this definition of isomorphism doesn't hold good here. So that means x1 and x3 are not D4 set isomorphic.